Swayam Prabha. Digital India. Educated India.
Okay, so we looked at transmissivity in yesterday's class, and so there can be surfaces or media which are non-opaque, which will allow some radiation to pass through, and now when radiation passes through such non-opaque media, generally they are participatory in nature because there can be emission because of the temperature of the medium being greater than 0 Kelvin according to Provost's law. It can also absorb, it can also scatter. Scattering is basically reflection, but scattering is from the volume. So scattering is of two types. There is in scattering, that is reflected inside, and out scattering is that which is going out. So the net will be scattered, whatever is scattered out minus whatever is scattered in. So this scattering could be a function of wavelength, and the scattering should be can be also be a function of the angle, okay, if it is not isotropic. So if you have anisotropic spectral scattering and all that, and so the what will determine the scattering? Scattering will depend on what, apart from the angle and this thing. For example, surface in a volume, for example in the atmosphere, it should depend on the size of the particle, okay. So the scattering by a dust particle will be different from scattering by a water molecule, which will be different from scattering from ice, and these ice can be of different shapes. We need not always assume that it will be spherical. If it is oblate and if it is non-spherical, then the scattering theory becomes very involved. So radiation heat transfer people as well as optics people and physicists have worked out extensive theories to handle scattering. So this is called Mie scattering theory, Rayleigh scattering theory, and so on, okay. So there are algorithms which have been developed, we call the T matrix algorithm and all that, which can handle scattering. So scattering is very involved. If you are doing such kind of calculation, you are in the forefront of radiative heat transfer research. You are able to handle scattering in molecules, scattering in the atmosphere and all that, okay. Now we look at some simple problems, so that whatever concepts we have learnt in yesterday's class and whatever definitions we have learnt, essentially they are reinforced, okay. Problem number 15. Please take down this spectral distribution of alpha as well as rho, okay. So only one wavelength is given, that is 1.5 micrometer, alpha lambda and rho lambda are given, okay. Once you are through, you tell me, I will start dictating the problem. Okay. All right. Problem number 15, the spectral absorptivity alpha lambda. The spectral absorptivity alpha lambda, the spectral absorptivity alpha lambda, and the spectral reflectivity rho lambda, and the spectral reflectivity rho lambda for a diffuse surface are given in the figure. For a diffuse surface are given in the figure. Alpha lambda and rho lambda for a diffuse surface are given in the figure, full stop. A, sketch the spectral transmissivity distribution. A, sketch the spectral transmissivity distribution. A, sketch the spectral transmissivity distribution. B, if solar radiation, B, if solar radiation with capital G, okay, if solar radiation with G equal to 800 watts per meter square, 800 watts per meter square. So if solar radiation with G equal to 800 watts per meter square and spectral distribution and spectral distribution corresponding to a black body and spectral distribution corresponding to a black body at 6000 Kelvin. Black body at 6000 Kelvin is incident on the material. Determine the fractions of the irradiation. Determine the fractions of the irradiation. Determine the fractions of the irradiation that are absorbed, reflected and transmitted by the material. That are absorbed, reflected and transmitted by the material. Problem clear? Okay. So, this is basically a fundamental problem where we move from one property to another property, and this is for the first time you will be calculating tau from tau lambda in this class, in this course. Okay. Please start. For the benefit of people who came late, for a surface I have given alpha lambda and rho lambda. So, solar radiation is falling on it. So, people who came late, alpha lambda and rho lambda are given. Incident radiation 800 watts per meter square, irradiation. Sun temperature 6000 Kelvin you can take. Sketch tau lambda and get alpha, tau and rho, and hence find out the fractions.
Alpha lambda plus rho lambda plus tau lambda will be equal to 1. Just alpha plus rho plus.
No, alpha lambda plus rho.
And alpha lambda plus tau, that also will be equal to 1.
Which one?
All only total emissivity quantities will be sum to 1 or directly multiplication.
Total will be also equal to 1. That can be proved from the derivation itself. Okay. So, the first part of the question is, the first part of the question is, from these two distributions we have to get the distribution for tau lambda. So, the basic equation we use is this comes from energy balance. This is with regard to the incident radiation. Okay, do not worry about the emission, do not get confused. Emission is a separate story. Tau lambda. So, up to lambda equal to 1.5, from 0 to 1.5 what is the story? This is 0.25, this is 0.125, 0.375 will be the sum. So, 1 minus 0.375 is 0.625. Okay. Where will that fellow come? Here. After that, E is already 1, this 0, therefore it is . Got it? We do not have to determine the transmissivity, but at least two properties must be known, right? Okay. Now we go to part B. What is part B? We have to get the individual properties. So, I have to get alpha, right. I have to get at least 2 of the 3 properties. So I just cannot get rho and say that tau equal to 0 and, but I know the f function from the f function charts. If I apply it once, I can calculate 2 properties, correct. So first we will write the formula for alpha. I can also write this as is it okay. Okay. Now we will keep this. I will start erasing from here. So correct. Okay. Now to get this 0 to 1.5 divided by 0 to infinity, what do I use? I use the f charts or f function chart. So t is already given that T equal to 6000 Kelvin. What is this? 0.89. Okay. Once you have this, so alpha is it correct? 0.332. So the absorptivity of the surface is 0.332. What absorptivity is this? Solar absorptivity. Okay. If it is absorbing radiation, let G be 800 watts per meter square, but if it is coming from from a source at some other temperature, it will change because it has got a spectral characteristic. Okay. That is why we are able to employ what are called selective surfaces. What is a selective surface? A selective surface is one which will have poor emission in the infrared and high absorptivity in the solar part of the spectrum. For what application do we want a surface like that? For so flat plate collector, we want high solar absorptivity and poor emission. It is possible to have some surfaces like this, but if it is a sun control film, in this room and those windows you want to put sun control film, or in your car you want to reduce the radiation and all that, then it is a transmittance or transmissivity we are talking about. By the way, we have introduced the quantities as reflectivity, absorptivity and transmissivity. Some authors, if you look at some books, they will say reflectance, transmittance and absorptance. It is essentially the same, it is basically nomenclature, there is no difference with. Okay, so the transmissivity of this glass, what happens is the transmissivity cannot be changed. In the sun control film we will see in the next problem, but the range of the wavelength range, a band in which it will transmit is different. It will cut out certain wavelengths. Okay, it acts like a pass filter. Therefore, overall you will get of the solar radiation certain portion is cut. They claim no 40% cut, 50% cut and all that, but that you can see that actually this thing is coming down, but from inside you can see outside, from outside you cannot see inside. Okay. Now you have calculated the alpha. Similarly, rho, okay. Do not quickly declare that rho is equal to 1 minus alpha, then you are doomed. Okay, there is a transmissivity in this problem. Okay. So rho, what was rho here? Is it correct? How much was it? Okay, so can you fill up this? In fact, I called it as G. I asked you only the fraction, but it is good to put everything in terms of watts per meter square, nothing wrong in doing that, because already by determining alpha, rho and tau we got the fractions. If you want to reword the problem. Vikram, you finish? Yeah. What is this I absorb? I reflected 88 point, I transmitted  okay. So I can develop the problem further and all that, but I leave it here. I can say part C, if the surface is at a temperature of 325 Kelvin, what is the emissivity of the surface? Part C. Part D, what is the net radiation heat transfer from the surface? Okay, we can keep on developing the problem, but now it is sufficient for us because we know how to calculate tau. Now we will solve a problem where we consider two surfaces, plain glass and tinted glass, so that you are able to appreciate, you are able to evaluate whether there is any benefit of using tinted glass. They are also claiming, no, in your glasses also you have tinted glass, photochromatic and all that, right. Let us see whether there is any benefit in doing that. Is this problem, is this clear? Okay.
Question it is given that radiation corresponding to black body at 6000 Kelvin is also incident on the surface.
G800 and which is equivalent to this thing. Okay, how else you want to do? You are thinking that apart from this something is there. No, even if I tell black body at 6000 Kelvin, how will you actually calculate? How will you actually calculate? You want to integrate from 0 to infinity. That is 1353 watts per meter square, man, that is coming from this thing, and then it falls into the atmosphere and this thing. So many stories are there for that. That does not exactly reach. Okay, black body for 6000 Kelvin, then from there, so you can calculate the solar constant from there, atmosphere, so many things are there. He is having a very important doubt. Many of you should have got this doubt, and it must have made you uneasy and all that, but luckily somebody has opened it up. Basically, there is nothing wrong in our first of all, there is nothing wrong in that question, but so it is my responsibility to clarify. We are not saying that it is actually, the radiation is actually from a black body at 6000 Kelvin. The nature is corresponding to the black body at 6000 Kelvin. If I know 800 watts per meter square, that the variation is like that. Since I am using only the F function chart, I am using it in the numerator and denominator to find out what is the band between lambda 1 to lambda 2, what is the fraction. So to the limited extent that using this information, I will be using the F function chart. This it's okay for me to consider this source to be a black body at 5800 Kelvin, but it is quite different from actually the irradiation coming from a black body. At the nature of the distribution is like that. Qualitatively, with lambda the irradiation varies like this. So it helps me only to calculate alpha, rho and all that, but if you want to know how much is reflected, how much is transmitted and so on, I need to know how many watts per meter square is incident. Are you getting the point? With just the information that it is a black body at 6000 Kelvin, it will lead to erroneous answers. I may get 1353 or something. For that I require other information. What else do I require? The diameter of the sun, diameter of the earth, the distance between, so many things I require. Why do you want to get into all this? If I do all this, you will get that 1353. That is a solar constant, but that 1353 is just which is entering outside the earth's atmosphere. Then so many things are happening because of carbon dioxide, water vapor, so many things, and it's okay, fine. Same thing with the transmissivity also. This black body story helps us to use the F function chart and get the properties. Okay, fine. Now we will solve another interesting problem. Problem number 16. The spectral transmissivity of plain and tinted glass. The spectral transmissivity of plain and tinted glass can be approximated as follows. Okay, plain glass. Okay, it was a transmissivity of 0.9 in the band 0.3 to 2.5 micrometer. Okay, what about this tinted glass? Same thing. So tinted glass is also 0.9. What's the big deal? Why everybody is trying to sell the tinted glass? Why is the tinted glass more expensive? The range must be more or less transmittance. It should have a same transmissivity over a narrow spectrum, narrow band. In fact, it has only between 0.5 to okay. Okay. So, the spectral transmissivity of plain and tinted glass can be approximated as given on the blackboard. Outside the specified wavelength ranges, the spectral transmissivity is 0 for both the glasses. Outside the specified wavelength ranges, the spectral transmissivity is 0 for both the glasses. A. Compare the solar energy that could be transmitted. A. Compare the solar energy that could be transmitted through the two glasses. Do not get confused though, it is not one after the other, okay. Compare the solar energy that could be transmitted through the glasses. Hang on. B. With solar radiation incident on the glasses, compare the visible radiant energy that could be transmitted. Compare the visible radiant energy that could be transmitted by the two glasses. Okay. There are 4 parts to this problem, because part A 2 calculations, one for plain and tinted, part B 2 calculations for plain and tinted. So, please start solving, I will take attendance and we will complete this problem, and with that the story of the properties is over. Shall we start solving? So, first A, plain glass. So, tau correct, but I do not know how I lambda I varies with lambda, but I have equivalent information. What is it information? I lambda is qualitative equal to that irradiation from a black body at 5800 Kelvin, that is the sun's temperature. Therefore, now I can get rid of this. Okay. So, 0 to 0.3 I do not have to worry about the integral and all that, right. Okay. Now, to do this, so what did you take T as? I have taken 5800, okay. We will take, everybody is, how many of you have taken 6000? Okay. So, 6000 is easier, no? But the correct temperature is only 5800. Okay. Let Ts be we have to get 0.3 lambda 1, right? F of 0 to lambda 1, Sampath, how much is it? 0.03. F of 0 to lambda 2, nine to lambda 1 to lambda 2, 929. So what is tau? 0.84 or 86? 84, huh? Okay. I wrote it to the purpose so that you don't get confused, 1 minus into 0 and all that. I made it complete. Second term alone is important. Fine. Okay. Now tau equal to 0.86, huh?
0.56. This one 0.8.
0.84.
0.84.